Hello everyone, this is Rohan, and in this video I am going to demonstrate how to find out the slopes and deflections in a overhang beam using conjugate beam method. Since this is the fourth lecture of this conjugate beam method series, I highly recommend you to please first go through the first three videos, the links of which I have posted in the description below. It will be very useful for you to follow this video. Alright, having said that, let's see today's problem, that is, find the slopes at A, B and D and the deflection at C and D of the beam as shown in figure. Take constant EI is equals to 4.5 into 10 raised to the power 3 kilonewton meter square throughout the beam. Okay, so today we have a overhang beam ACBD having a hinge support at a hinge support at B, and a free end at D. Portion AC is 4 meter, portion CB is 4 meter, and the overhang portion BD is of 1.5 meter. At the point C, there is a 25 kilonewton point load, and at the end point D, there is a point load of 8 kilonewton. And throughout the span, the value of EI is constant, that is 4.5 into 10 raised to the power 3 kilonewton meter square. Now, this is what we call as the real beam, and the first step to solve any problem using conjugate beam is to convert the real beam into a conjugate beam. A conjugate beam is a fictitious beam of the same length as the real beam, but the supports are altered in a way. Okay, so now if there is a end hinge support in the real beam, it remains as a end hinge support in conjugate beam. If there is an intermediate hinge support in the real beam, it becomes a internal hinge in the conjugate beam, and if there is a free end in the real beam, then it becomes a fixed end in the conjugate beam. So as you can see here, this is your conjugate beam and this is the real beam. Now we will have to move on to find out the M by EI diagram of the real beam having these two loads. So for that, what I am going to do is I am going to use the principle of superposition, wherein I am going to take one load at a time. That means this beam is equals to only this load and neglecting this load, plus the same beam with only 8 kilonewton and neglecting this load. So this I'll call as loading 1 and this I'll call as loading 2, and I will find out the M by EI diagram of these two loadings separately, and then I'll merge them. Okay, then let's move on to loading 1 on the real beam, that is only 25 kilonewton, and here at D there is no load. All right, so in order to find the M by EI diagram, first of all we'll have to find out the support reaction VA and VB. And how to find that? Simply by using the equations of equilibrium. So let's start. First of all, I'll use summation of moment about B is equals to 0, and I will take clockwise as positive. Okay, so here I'll have VA multiplied by 8, that means 4 into 4, and minus 25 into 4 is equals to 0, right? So here if I solve this, I'll get VA is equals to 12.5 kilonewton, and since this is positive, our chosen direction is correct, so therefore I will directly write here as VA equals to 12.5 kilonewton. In order to find VB, I can simply use summation of f of y is equals to 0, and I am taking upward force as positive. Therefore, we'll have 12 plus 12.5 minus 25 plus VB is equals to 0. And if I solve this, I'll get VB is equals to 12.5 kilonewton. And again, since this is plus, our chosen direction is correct. So therefore, I can directly write here as 12.5 kilonewton. All right, this is enough for us to find out the M by EI diagram due to loading 1 on the real beam. I'll find out the M values at all these 4 points and then the order diagram. Of course, we know moment at A will be 0. Now what will be the moment at C? Moment at C will be 12.5 multiplied by 4, that is nothing but plus 50 kilonewton meter. Now, with our general knowledge of structural analysis, we know that moment at B and moment at D will be 0. Still, I have shown these two steps. I'll not explain it. You can refer very easily these steps and understand this on your own, how at M at B and M at D becomes 0. Alright, now let's move on to the diagram. How do I draw the diagram? Of course, at A it is 0, at C it is 50, but let's not forget, now I have to draw the M by EI diagram. So I have to draw it for 50 divided by EI. Alright, so at A it is 0, at C it is 50 divided by EI, at B again it is 0, and at D it remains as 0. Now this whole diagram will be positive. So this is the M by EI diagram due to loading 1, that is 25 kilonewton at C. Now let us move on to loading 2 on the real beam, that is 8 kilonewton at the point D, and I'll have to find out the M by EI diagram due to this load. For that also, first I will need to find out the support reaction VA and the support reaction VB. Again, what is the procedure to find out support reactions? Simple, equations of equilibrium. So now this time I will take summation of moment about A is equals to 0, and I'll take clockwise as positive. So therefore, now this 8 kilonewton is going to have a clockwise moment at A of 8 multiplied by 9.5. It is 1.5 plus 4 plus 4, that is 9.5. 8 into 9.5. And VB is going to have a anti-clockwise moment, right? So VB multiplied by 8. So 8 into 9.5 minus VB into 8 equals to 0. So that gives me VB is equals to 9.5, and since VB is positive, therefore my chosen direction is correct. So I can write here VB is equals to 9.5. Simply now I can find VA by using the second equation of equilibrium, that is summation of Fy is equals to 0, and I am going to take upwards force as positive. So therefore I'll have minus 8, I'm starting from right to left, minus 8 plus 9.5 plus VA is equals to 0, or VA will be minus 1.5 kilonewton. Now since I have got the value of VA as minus, so my chosen direction of VA is wrong. Simply what I'll do, I'll erase that VA and I'll show the VA in the opposite direction, and this is 1.5 kilonewton, right? My chosen direction was upwards, but while calculating I found out that VA is coming as negative, so therefore my chosen direction was wrong, so I have corrected it here. All right, now this is enough for me to draw the M by EI diagram due to loading 2 on the real beam. Similarly, I will find out the M values at A, C, B and D. All right, so moment at A, obviously end hinge support is here, so MA will be equals to 0. What will be MC? I'm coming from left to right, just see that it will be minus 1.5 into 4, 1.5 into 4, so that is minus 6 kilonewton meter. Next I'll find out at B. What will it be? It will be minus 1.5 into 8, minus 1.5 into 8, so therefore it will be minus 12. And needless to say, at D it will be 0, but still I have shown you how it is coming as 0. So again, with the help of these values I can draw the M by EI diagram. Starting with A, it is 0. At C it is not minus 6, it is 6 by EI. Okay, this is M. I have to draw the M by EI diagram. So this is minus 6 by EI. At B it is minus 12 by EI, and at D it is again 0. So this entire diagram is negative, right? And therefore this is the M by EI diagram due to loading 2 on the real beam. So we had M by EI diagram due to loading 1 and M by EI diagram due to loading 2. Now we will have to apply these M by EI diagrams as loadings on the conjugate beam. So again, in this slide, I have brought back the conjugate beam. So let us see what is the loading 1 on the conjugate beam, not to be confused with our original loading 1. Loading 1 of conjugate beam is the M by EI diagram of loading 1 on real beam. That is nothing but this. Now, this M by EI diagram was positive. Now, if the M by EI diagram is positive, then the loading is in the upward direction. This is according to the sign convention. This has been discussed in the lecture number 1. All right. And now this is loading 2 on the conjugate beam, which is nothing but M by EI diagram due to loading 2 on the real beam. This diagram is there 6, 12, 0, and this entire diagram was negative. So therefore, the loading will be in the downward direction following the same sign convention as said before. Now, before we could move on to find out the slopes and deflections using the shear force and bending moments, we will have to first find out the support reactions in the conjugate beam, that is VA, VD and MD. And you know, in order to find out the support reactions of a beam having internal hinge, we need to take equal and opposite forces at the internal hinge, and we'll have to separate out these two beams and we will have to solve this part by part. So ultimately our unknown is VA, VD and MD, but in order to solve this we will have to consider this V dash B in downward direction I have chosen, and upward direction V double dash B. All right. So now just see that I will first consider the left hand portion of the beam, that is the AB part of the conjugate beam. Here in if you see my previous videos, I have taken the beam and the loading separately. However, some of my students have told me that they are having certain difficulties in imagining how this dynamics is actually working. So here I have changed my approach and I am going to put the loading on the beam. However, my personal opinion is that it looks really clumsy, but if it makes my students understand things better, I am all for it. All right, so here in this slide, I am taking out the portion AB of the conjugate beam, and now I will start applying the loading. What were the loading on this part? First loading was this 50 divided by EI in the upward direction. Okay, just refer my previous slide for this. And the next loading was this 12 divided by EI, this UVL. Okay, was there as the second loading. Okay, so these two are the loadings on the portion AB of the conjugate beam. Please see BD portion has been neglected. So what is the reactions here? One is VA that we have to find out, and the second one is VB dash. These two are the reactions that we have to find out now. How to find out support reactions? Again, we will have to use the equations of equilibrium. So let's first go for summation of moment about B equals to 0, and I'll take clockwise moment as positive. Okay, so now here I'll have minus VA into 8 since this is anti-clockwise. Now, due to this 50 divided by EI, this loading, what will it be? Of course, this is in the clockwise direction, so this is positive. So half into 8 into 50, this is half into base into height, multiplied by the CG. Now, please see, if you have a triangular load like this, from B, what will be the CG? The CG is somewhere here. That means it is halfway through this. So here the CG is half of 8. The CG is half of 8. Okay, now just see for the lower part, this is again in the anti-clockwise direction, so therefore this is minus half into base into height, that is half into 8 into 12 divided by AI multiplied by the CG of this triangle will be what? 1/3 of base, that is 1/3 of 8 equals to 0. If you solve this, you will get VA is equals to 84 divided by EI, and since this has come out to be positive, so therefore my chosen direction is correct. So I can directly write here 84 divided by EI. Alright, now how to find out V dash B? to use the equation of equilibrium, summation of f of y is equals to 0 upwards as positive. Now here let's go from left to right. Minus 84 divided by EI plus, I'll take this triangle, that is half into 8 multiplied by 50 divided by EI. Then this triangular load, that is minus half into 8 into 12 divided by EI. And lastly, minus V dash B is equals to 0. If you solve this, you will get V dash B equals to 68 divided by EI. Again, since the value here is positive, therefore my chosen direction is correct, that is downwards. So here I can directly write 68 divided by EI. Now, having known this, I can now consider the right portion of the internal hinge, that is BD of the conjugate beam. Here we have an internal hinge B and a fixed support D, and the loading on this part is just this small triangular load 12 divided by EI for the span of 1.5. And what are the, okay, now from the previous slide, what do we know? That the value of V double dash B is 68 divided by EI in the upward direction. Why? Because V dash B was 68 divided by EI in the downward direction. So at the internal hinge, you know, the shears are equal and opposite. So since V dash B was 68 divided by EI in the downward direction, so therefore V double dash B will be 68 divided by EI in the upward direction. Okay, so what are our unknowns here? Our unknowns are VD and MD. Please understand, both these directions are assumed. If any of these values come as negative, I'll simply change the direction. All right, how to find out support reactions? Equations of equilibrium. So let's start. Summation of f of y is equals to 0 upwards as positive. So starting from left, I will have the upward force of 68 divided by EI, then minus of this triangular load, that is half into 1.5 into 12 divided by EI, and finally minus VD is equals to 0. If I solve this, I'll get VD is equals to 59 divided by EI, and since this is coming as positive, my chosen direction is correct. I can directly write here as 59 divided by EI. In order to find out the moment, MD, I'll go for the equation of equilibrium as summation of M of B equals to 0, and I'll take clockwise as positive, and I'll go from left to right now. Excuse me. Minus of MD, because this is anti-clockwise, right? Then VD will have a clockwise moment here, so plus 59 divided by EI into this distance 1.5, and then again this load is going to have a clockwise moment across B, so it will be half into base into height, that is half into 1.5 into 12.5 multiplied by the CG. The CG is at a distance 1/3 of 1.5, and all of this is equal to 0. So MD will be equals to 93 divided by EI, and since this has come out to be positive, therefore my chosen direction is correct. So I can directly write here as 93 divided by EI. All right, so having known having known all the unknowns of the conjugate beam, let us now draw this diagram. Just see, students, here is your conjugate beam ACBD. This is the loading 50 divided by EI, this is the loading 12 divided by EI, and these are the three support reactions that you have found out. The two problems that I had solved separately, I had taken loadings and the beam separately. I hope you are able to easily understand when I have taken this all in one diagram. Now with the help of this, I am well equipped to find out the slopes and deflection at any point here. So let's start one by one. The first thing that is asked is slope at A in the real beam. Slope at A in the real beam is nothing but shear force at A in the conjugate beam. What is the sign convention for shear force? Left of section downward force is negative. So therefore here I can directly write the shear force at A in conjugate beam will be minus 84 divided by EI. The value of EI is given, and if I calculate it, I get it as minus 0.0186 radians. Now what does this minus sign indicate? It indicates that the slope here is in the clockwise direction. So the slope of A in the real beam, that is theta A, is 0.0186 radian in the clockwise direction. Next, slope at D in the real beam. It is nothing but shear force at D in the conjugate beam. What is the sign convention for shear force? Right of section downward force is positive. So therefore, I can directly write here it is equal to 59 divided by EI. The value of EI is put here and calculated. And what does this positive sign indicate? The positive sign indicates that the slope is anti-clockwise. So slope at D in real beam is 0.0131 radian in the anti-clockwise direction. All right. Now, same figure, moving on to the third slope that has been asked, that is slope at B in real beam. Slope at B in the real beam is nothing but shear force at B in conjugate beam. I am going to calculate the shear force at this point starting from left. That means I have to follow the right of section sign convention. That is, downward force is taken as positive. All right. So here, what is the first downward force? That is 59 divided by EI. Yes, that is positive. And then this small triangular load, again this is in the downward direction, so it will be positive. So half into base, that is 1.5, and height, that is 12 divided by EI. So if you calculate this, you get this as 68 divided by EI. Putting the value of EI, I will get the value as 0.0151 radian. And what does this plus sign indicate here? It indicates that the slope is in the anti-clockwise direction. Okay, so the slopes at A, B and D were asked, and all those slopes have been found out. Now coming on to the deflections. Okay, so now it has been asked deflection at D in the real beam. Deflection at D in the real beam, YD, is nothing but bending moment at D in conjugate beam. And what will be bending moment at D? It is nothing but only this load, this moment, that is 93 divided by EI. And what is the sign convention? Right of section right of section anti-clockwise moment is taken as positive. So this is 93 divided by EI positive. Putting the value of EI, I can get the value of 0.020 meter. Okay, now what does this positive sign indicate? It indicates that the deflection at D is in the upward direction. So here I will write the final answer as 20 millimeter in the upward direction. 20 millimeter in the upward direction. And finally, it has been asked to find out the deflection at C in the real beam, YC, which is nothing but bending moment at C in the conjugate beam. So therefore, let us revise how to find out the bending moment from left of section. Left of section, clockwise moment is taken as positive. So clockwise bending moment is taken as positive, and anti-clockwise bending moment is taken as negative. So with that, let's see one by one. So therefore, minus 84 multiplied by 4. And now I'm going to take this small triangle 6 meters, sorry, 6 divided by EI, that is up to 4 meters. So that will be minus half into 4 into 6 divided by EI, that is half into base into height, multiplied by the CG of this triangle up to C, that is 1/3 of 4, 1/3 of 4 meter. Okay. Third, I'm going to take this triangle here, this one half triangle, right? So it will be plus, since it is clockwise, half into base, that is 4, into height 50 divided by EI, and then I have to multiply it by the CG of this half triangle, this one from C is 1/3 of 4, 1/3 of 4. So if I calculate that, I get that as minus 218 divided by EI. Putting the value of EI, I'll get minus 0.048 meter, and the minus sign indicates that it is in the downward direction, 48.44 millimeter in the downward direction. So here, lastly, as I always like to show you the original shape and the deflected shape. So the original shape, this was of the real beam. Now these are the three slopes that we had found out, and these are the two deflections that we have found out. And based on this data, I'll be drawing the deflected shape. Here the original shape is again drawn by dotted lines, because now we will have to draw the deflected shape. Using this data, the deflected shape goes something like this. Okay, let's see point by point. A remains at A because there is no vertical deflection here. However, there is a slope which we will see later. C has come down to C dash by a distance YC. Just see the value of YC. There is some value and it is in the downward direction, which is shown here. Okay. B again has no deflection, since it is a hinge support here, no vertical deflection. However, it has some slope which we'll again see later. And this point D has gone up to D dash by a distance YD. Here you can see the value of YD, the direction is in the upward direction. So YC, downward direction from C to C dash, and YD, D to D dash, is in the upward direction. Now let's check out the slope at A. So if this was the original direction of A and this is the deflected direction, then the deflection should be in the clockwise direction. Yes, and this also correlates to this, what we have found out, theta A is in the clockwise direction. If you look at theta B, if this was the original position and now this blue line is the deflected shape, so therefore the slope must be anti-clockwise. Yes, and that is what is shown in this data also, that the slope at B is anti-clockwise. In order to show the slope at D, let us draw one virtual horizontal line here so that we can easily see. So if this was the original position, then if I have to come here, so then again it will be in the anti-clockwise direction, and that is what correlates to this data that we have got also. So with the help of the diagram also, I hope I have shown you how to find out the slopes and deflection at various points of a overhang beam using conjugate beam method. If you have any doubts, you can ask me in the comments below. Thank you for your time.